Welcome back. Now we come to standing waves in strings and pipes, the theory, and then I'm going to build on what I covered last time. The last time we saw that x equals n lambda over 2, where n equals 0, 1, 2, 3, 4, will satisfy the nodes of the waves, and x equals n lambda over 4, where n equals 1, 3, 5, 7, 9, will satisfy the requirement for antinodes in a wave. So let's first cover the topic of strings, standing waves in strings, and also pipes closed at one end and closed at the other end. So it could be closed here and closed here, closed both ends, and then it could be open at either end. Open at either end. Okay? What we're going to see that the required frequencies of harmonics for these closed at both ends, open at both ends, and also the strings, it's going to be the same, because what's going to happen is that for strings, the two ends are going to be fixed and they're not going to be oscillating up and down. So the requirement is going to be that the two ends are fixed, and therefore the two ends are going to have to be nodes, right? The closed end, the two ends are closed, and they're also going to be nodes, right? Like this, and then the two open ends are going to be antinodes, right? So when we have this situation, this is called the boundary condition, and the boundary condition is that this is the length of the string like this, and this is the length of the pipe, and the boundary condition is that the two ends are both nodes, right? This is a famous topic in physics, boundary conditions, and we see this in all kinds of wave theory, including quantum mechanics. So when I cover the topic of quantum mechanics, you see how boundary conditions will play a role in that also. Say x is equal to L n lambda over 2. So this is the boundary condition. Why? Because the length of the string is L, or the length of the pipe is L. So then from this, what kind of relationship do we get? We get L is equal to n lambda over 2. Therefore, lambda is equal to 2L over n. N is equal to 1, that means the wavelength is equal to 2 times the length, and therefore the length is equal to half the wavelength, right? So what kind of a harmonic is that? That's called the n equals 1 harmonic, right? That means in the length of the string, you are able to fit half of a wavelength. A complete wavelength is up, down, and back up, right? So half a wavelength, and then this is the half a wavelength also. So the wave will be oscillating like this. The two ends will be nodes, 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 and then this middle will be antinode, right? So this is the n equals 1 harmonic. When n is equal to 2, what do we get? For n equals to 2, we get the wavelength is equal to 2L over 2, which is just L, and therefore the length is equal to the wavelength. So that means the string will go up, down, and back up, and then coming back, it'll go up, down, and back up. So then these 2 points will be antinodes, antinode, antinode, and then this point will be node, this point will be node, and then this point will be node also, right? But the boundary condition that the two ends are nodes are still satisfied, right? So n equals to 3 is equal to lambda is equal to 2L over 3, and therefore we have L is equal to 3 halves of a wavelength. So that means you're able to fit 1.5 waves, right? So the string will go up, down, up, and then back again, up and down, right? So then it'll go like this. So this one is equal to n is equal to 2 harmonic. And this is also called the first overtone. First overtone. And then this one is the n equals 3 harmonic. And it's also called the second overtone. And then so on and so forth. For n equals to 4, the wavelength, the length of the string will be twice the wavelength, and you'll be able to fit up, down, up, and then back again, up, down, up, and then it'll go like this, and you'll be able to fit 2 complete waves, right? Closed at both ends is this exactly the same. It'll go up and then down and up, and then all the other harmonics will look exactly the same. How the picture look for the pipe open at both ends, right? So then, now the picture will look different, but the harmonics are actually the same. The two ends are antinodes, and antinode means it's maximum vibration, so it goes from up here all the way to down here, and it goes from down here to all the way up there, right? So this is n equals to 1. But if you really look at it, this is still, the length of the string is half the wavelength. If you look at a wave, it goes up, down, up, right? But this one is starting at the up position here, and then it's going all the way to the down position here. Well, this is still half of a wavelength. So that means the pipe's length is still equal to the, from the maximum peak here to the valley, and it's still equal to half the wavelength. And then it starts from down here, so it goes like this, and then it goes like this, and then like this. So this portion from here to here is the length of the pipe, right? And it's still equal to half the wavelength. The other harmonic will look like this. It starts with maximum and goes down and then back up, and it starts at the minimum, goes up and back down. So what is that? Well, it's starting here, up here, then it's going down all the way to here, then it's going all the way up. So it's going all the way back to up. Well, that's still a complete wave, right? Lambda over 2, so the whole thing makes for a complete wave, and therefore this is the n equals 2, the length of the pipe is equal to a complete wave of the sound wave, right? So it's still equivalent, even though it looks a little different than the string picture, but the harmonics are still the same in the sense that the length of the pipe is half the wavelength of the wave, the length of the pipe is the complete wavelength of the wave, and so on, right? Now we can solve for the required frequencies of the sound waves that will resonate in these pipes. And then we can put the wavelength here, 2L over N. And then we can solve for the frequency, we get NV over 2L. And then N is equal to 1 is called the fundamental frequency. Right? The second harmonic because it's the n equals to 2, and then the first overtone is because it's over the fundamental frequency. So it's the first frequency that's over the fundamental, right? And it always is twice the frequency of the fundamental, right? Okay? So now let's go to the pipe that is closed at one end and open at the other end, right? So let's see what we will get for that one. And then what will this be? Well, this left side will be a node, and then the right side will be an antinode, right? So what is the boundary condition there? So we're gonna use the fact that the length is gonna give you antinode. So look at the equation that we had, that we wrote earlier, right? So now I'm gonna put here x is equal to L, n lambda over 4, and then I can calculate what the lambda is. Lambda is equal to 4L over n, where n is equal to 1, 3, 5, and so on. Now we could also calculate the required frequencies that resonate in this tube. We have B is equal to F times lambda, and then the lambda is equal to 4L over n, and then F is equal to NB over 4L. And then n is equals to 1, 3, 5, 7, 9, so on and so forth, right? So these are the required frequencies, but notice that they are missing the even harmonics, the n equals to 2, the n equals to 4. Well, they're missing the even harmonics just for the same reason that x equals n lambda over 4 was also missing n equals 2, n equals 4, and n equals 6, right? The requirement for antinodes, this one was antinodes. Okay, so what will n equals to 1 look like? N equals to 1. Well, n equals to 1 exactly looks like this, because why? We have n is equal to 1, lambda is equal to 4L over n, and then if n equals 1, lambda equals 4L. That means the wavelength of the sound wave is 4 times the length of the tube. And therefore, the length of the tube is equal to wavelength over 4. It goes up, down, up. A quarter of the wave is essentially just this much. It starts at the node and then goes to antinode. And then it could start at the node and go all the way to the bottom antinode. So it can go like this and then go like this. So that means you have a quarter of the wave only fitting in the length of the tube, right? So then that's what the n equals 1 looks like. How about the n equals 3? N equals 3, we have lambda is equal to 4L over 3. 4L over 3, that means L is equal to 3/4 of a wavelength, right? That means the length of the pipe is 3/4 of the wavelength, so it starts here at the node, goes to antinode, then goes all the way down, and then goes all the way to the bottom. So this is 3/4 of a wave right here. So how will that look like? Starts here, goes all the way up, and then back down all the way to the antinode, and then goes down all the way back up to the antinode, right? So this is a half a wavelength from here to here, and then this is a quarter of the wavelength. So you always have an extra quarter of the wavelength that's at the end of the tube. You see, quarter, and then in this case an extra quarter. So this is n equals to 3, so this is the third harmonic. Why? Because the second harmonic is missing. Even number harmonics are missing, right? But since it's the first one that is over the fundamental frequency, we call it the first overtone. First overtone. And it will be 3 times the frequency, right? N equals to 1 will give you F equals V over 4L. N is equal to 3 will give you 3 times the frequency, right? You put here lambda is equal to 4L over 5. Therefore, L is equal to 5/4 wavelength. So what does the picture look like for that one? Okay, so the wave goes all the way up, back down, and all the way to the node. Then you fit an extra quarter of a wave, right? So then it goes down, up, back down, and then you fit an extra quarter of the wave, right? So this one here is always the extra quarter of the wave that you are fitting. Makes 5/4 of a wavelength, which is a complete wave, and an extra quarter of a wave. So this one is equal to n equals 5, fifth harmonic, and second overtone. So summarizing the frequencies for this kind of a pipe, and then the way that the overtones go is that the n equals 3 is the first overtone, n equals to 5 is the second overtone, and n equals to 7 is the third overtone. There's instruments that go like this. Of course, the stringed instruments, violin, guitar, cello, and other string instruments will be the same harmonics as the string one that we covered. The tube that is closed at one end and open at the other, which is this one, closed at one end and open at the other, this one will be like reed instruments like the clarinet, and also the brass instruments like the trumpet. The closed end will be where you blow your mouth in. So quickly you pucker your mouth, you blow into the one of the ends, and then you close your mouth to create a closed end, right? And then the open end will be, for example, in the clarinet, whichever piece you push in, right? And then the air comes out of that end. The closed end is actually your mouth. When after you blow into it, you pucker your mouth and you close it, and to create a sealed end. Instruments that are open at both ends would be, for example, flute. Open at both ends, the flute. Instead of puckering your lips and putting it on the closed end and making a seal, you actually are blowing into the open end of the flute. You're going like that, and then you are opening a particular hole in the length of the flute to create standing waves, and that would be open at both ends, right? So a lot of these instruments that you hear and that you play are example of one of these kind of pipes or strings, okay? So next we will actually do an example of this. Thank you very much.